Hello, David. You are on mute. You are on mute, David. You are mute. Your microphone is on mute. On the bottom, there is a microphone sign. Turn it on.
Now it's okay.
Yes. Hi, David. How are you?
Well, pushing the pens. Yeah, I published a couple of papers. So this pen, you saw this. I have a new stuff in there, and actually, the wide problem in a magnetic field is quite interesting.
Okay.
Yeah. So it's the story of the magnetic field with,
and probably more people coming. Okay. So today we are pleased to have Onur Erten from Arizona State University. Onur did his PhD at Ohio State, working with Mohit and Nandini. And then he went on a postdoc in Rutgers, working mainly with Piers Coleman. It was the time that this new results on topological condo insulator came along, and he wrote multiple important papers which were addressing many confusing results on the material. After that, he spent a short time, stayed as a postdoc in Max Planck Institute in Dresden. He worked with different people, I think including Roderick Mosner. And then after that, he joined Arizona State as a faculty. The main parts of works of Onur are on correlated electronic systems, different exotic quantum phases, and also topological phases, in particular interplay of topology and a strong interaction. So thank you, Onur. Please, we are with you.
Thank you, Puyan. Good afternoon, and it's a great pleasure.
Hello.
Maybe mute David.
Yeah, David. Yeah. Okay.
It's a great pleasure to be giving the colloquium today, and I'd like to thank Puyan for the kind invitation and the introduction. So today I'll talk about superconductivity in nickelates, which is a newly discovered high temperature superconductor. Now I will compare and contrast with other well-known families of unconventional superconductors. So this work is done in collaboration with Emilian Nika, who's a postdoc in my group, Jyoti Krishna, who is a postdoc in my colleagues group, Antya Botana, as well as Rongyu from Renmin University and Chimiasi from Rice University. So I'll be mostly presenting these two papers. And that is the bulk of my talk. And if time permitting, I can talk about a bonus topic on Fermions and twisted van der Waals magnets. This is, again, it's not really related with the original topic of today's talk, but it is a new and emergent field, this twisted van der Waals systems. And if there's interest, I'll be happy to talk about it. So this is the work done with my student, Mohammed Akram. All right, and I would appreciate if there's any questions, please don't hesitate to interrupt me and ask anytime. So I don't have really that many slides, so I would like to have a lively discussion. All right, since this is a colloquium, let me start by telling you what is condensed metaphysics. So why are we doing what we are doing? So as many of you know, there are four fundamental forces in nature, and at least in our energy scale. And at some higher energy scale, they might be unified, grand unification, etc. But at least in our energy scale, there are four fundamental forces.
Hello?
Strong and weak.
I'm fine. I cannot talk now. I'm on Zoom.
David, can you mute
You can mute them too if you're, strong and weak forces tell us the properties of the nucleus and subatomic particles, and electromagnetism gives us chemistry, and the gravity is gravity. So if you're in small length scales or high energies, you can probe all these 4 forces. But let's say if you're in around angstrom length scale, you have atoms and molecules, right? And if you go to larger length scales or lower energies, around the micron scale, when the thousands of atoms comes together, something magical happens. You start having new collective behavior. You start having chemistry and condensed matter physics. For instance, you can have a Bose-Einstein condensation or crystalline phases like salt or lanthanum and copper oxide, for instance. And this continues if you go to higher and higher length scales. For instance, if you go to a millimeter scale, you can have some cute authors, or if you go to a kilometer scale, now you have sociology and economy. And you can see that all of this really arises from the 4 fundamental forces. But you have new degrees of freedom at every length scale and energy scale. Therefore, it's not possible to predict what's going to happen at, let's say, kilometer scale using solving the quantum chromodynamics, right? So the 4 fundamental forces cannot predict the Twitter trends. Therefore, whatever your length scale is, in order to understand the properties of your system, you have to distill the necessary ingredients to understand the complex phenomena. So this is the idea of emergence, and nicely summarized by Phil Anderson in his famous paper, More is Different. Unfortunately, Phil passed away a couple of months ago, which is one of the giants in our field. So this is the length scale that we are interested in today. We are going to talk about condensed matter systems. So this is a general introduction to what condensed matter physics is. So let me tell you a little bit about superconductivity. So, because this talk is mostly on superconductivity in the spirit of a colloquium. So most big discoveries, breakthroughs in physics are usually preceded by another discovery that is usually overlooked. In the case of superconductivity, this was the liquefying helium, the Camerlin-Onnes liquefied helium in 1908. This led to experiments for him to go to low enough temperatures that were not possible to go down to before. So he was go down to few Kelvin regime, and he realized that around 4 Kelvin, the mercury, this is the original plot from his diary, not diary, journal diary, that the resistivity of mercury jumps and goes to 0. So this is the first discovery of superconductivity. And superconductivity is such an unusual effect, that something that really we are not used to in our daily life. We are used to having the Ohm's law, right? We are used to having resistivity. So that's why, that's maybe one of the reasons it took about, 46 years to come up with a theory to understand superconductivity. So this is the theory of Bardeen, Cooper, and Schrieffer, the celebrated ECS theory. They argued that the weak interaction, or showed that the weak interaction between the electrons mediated by phonons gives rise to a Fermi surface instability. So instability meaning that this will happen regardless of how small the interaction is. As long as you have some effective weak interaction between your electrons on the Fermi surface, you will always have a superconductor as long as there's no other broken symmetry. So in this case, if this is your Fermi surface, the weak interaction between the electrons on the opposite side of the Fermi surface with time reverse partners forms bosons called Cooper pairs. In the BCS theory, these bosons have 0 net spin and 0 net angular momentum. So I will keep on saying S-wave superconductor, for instance. That would mean that there is no net angular momentum for these bosons. And one of the characteristics characteristic property of superconductors is the superconducting gap, which is effectively the binding energy of these pairs. So in the case of BCS theory, this is proportional to your transition temperature. And this is one of the most characteristic property of the superconductor because it can be seen experimentally in various techniques such as tunneling, specific heat, angle result photoemission spectroscopy, or other optical techniques. And if you have these L equal to 0 S-wave superconductors, the superconducting gap forms a clean gap. This would be like an S-wave superconductor. So this clean gap can be seen in all these experiments. Mainly you no longer have low energy fermionic excitations, and the low energy, the fermionic excitations comes from breaking these Cooper pairs, and then you create electron and hole-like excitations. So this is one of the characteristics of superconductors that can be experimentally seen. Another one is the fact that the superconductors breaks the U1 gauge symmetry, meaning that the order parameter now picks up a phase. This phase is the same phase of the U1 gauge symmetry of the electrons, and U1 meaning that it is a complex phase. And once you pick this phase, this is spontaneous symmetry breaking. And it has important consequences such as Meissner effect, Josephson effect, and or the Abrikosov vortices. So even though the discovery of superconductivity came by the resistivity going to 0, now in modern experiments, this is not good enough. So one has to also show that the system, if you claim a system is a superconductor, you also need to demonstrate the Meissner effect, which is the perfect diamagnetism of the superconductor. All right, so if there is no questions, I will move on. So this is my introduction on superconductivity, and anything that obeys the BCS theory are called conventional superconductors, meaning that we understand them. So BCS theory works so well that people even use BCS theory to understand phonons in metals. So this is such a remarkably successful theory. One of the most successful theories that we have in physics. I don't know if he's talking. I think David might be talking, but he's muted. I don't know. Anyway, so what I'm trying to say is, let me close this. Anything that obeys.
Let me ask David. David, if you want to talk, you have to unmute yourself.
There is a additional criteria in a BCS theory that the gap and the temperature is a constant number, which is a feature of the BCS.
Right, absolutely. So this is what I was trying to say. The transition temperature and the superconducting gap are proportional to each other.
Yeah, what's our number? 3.2, I think.
Right, something like that, yes.
Yeah.
Yes. So the transition temperature is, in the BCS theory in this case, is set by the e to the -1/g, where g is your coupling constant, something like the density of states times the electron phonon coupling. And omega is the Debye frequency, which gives you the transition temperature that is proportional to your superconducting gap. And looking at this proportionality, you can say how well your superconductor fits in the regime of BCS superconductors. And small deviations from this ratio tells you maybe it's not exactly like BCS theory, but you can do corrections to BCS theory, so-called Eliashberg theory, which works really beautifully for strongly coupled electron phonon systems like MgB2, for instance. That gives you very, very remarkably well results. So the conventional, to sum up, conventional superconductors, which are practically all the metals that we have, the BCS theory works beautifully well. But at the same time, the transition temperature for the BCS superconductors are usually very, very low because mainly it requires a weak interaction. So, but if we want to find superconductors that have higher transition temperatures, then we need to look for other classes of systems that does not necessarily belong to the BCS theory. So just to define it, I'm saying that everything fits the BCS theory. I'm going to call it conventional. And anything that does not fit the BCS scenario, I'm going to call it unconventional superconductors. So let's talk about unconventional superconductors because the main topic of this talk is unconventional superconductivity. So the first unconventional superconductor that discovered is the cerium copper 2 silicon 2 in 1979. In this case, the TC is not really that high. So you might say, how do you know that this is an unconventional superconductor? Why is this not a BCS superconductor? Actually, we know, and people knew very soon after the discovery of superconductivity in cerium copper 2 silicon 2, it's not a BCS superconductor because the Debye frequency exceeds the Fermi energy. Even though I didn't get into details, for the phonons to give rise to an effective attractive interaction, you need retardation effects, mainly the phonons. Normally, the Coulomb interaction is much greater than phonons, but because the phonons, even though the Coulomb interaction is repulsive, and the phonon attraction due to phonon is attractive, but for the phonons to be able to lead to superconductivity, you need this phonon attraction due to phonons to be retarded in time. Mainly, it is delayed in time. If it exceeds the Fermi energy, it's no longer delayed in time. Therefore, you cannot have an effective attractive interaction. This mainly puts a strict bound for BCS superconductors because you want a high Debye frequency for high TC, but if the Debye frequency is high, then you actually kill your attractive interaction immediately. So it was soon realized that the cerium copper 2 silicon 2 is not really a BCS superconductor. But what really kicked off this field is, and by the way, the symmetry of the order parameter here is still under debate. It's quite surprising. People thought it was D-wave for many, many years, over 30 years, but recently they realized that it's actually fully gapped. And it's not really clear what is the form, the symmetry of the order parameter. It's for sure it's not an on-site S-wave superconductor, so what can give rise to fully gap superconductivity in cerium copper 2 silicon 2 is still under debate. But what really kicked off the field in the study of unconventional superconductivity are the cuprates.
Onur, just a quick question. Only in this compound or in many other cuprate family, it's also questioned whether they are D-wave?
I think cuprates, people agree it's D-wave. In heavy fermions, usually the gap is much smaller.
Okay.
So if your TC is half a Kelvin, it kind of looks like, let's say you are looking at some experimental probe like RPES or I don't know, specific heat, etc. They would always, D-wave superconductors would have a V-shaped density of states, which you can deduce from temperature dependence of these probes. But in cerium copper 2 silicon 2, it looks like D-wave, but at very low temperatures, actually close to, close to zero temperature, it becomes fully gapped.
Okay, thank you.
So it's not really clear. So what really kicked off this, excuse me, the field of unconventional superconductivity is the discovery of cuprates or copper oxide superconductors. Because these guys have TCs that are on the order of 140 Kelvin. So it's much higher. Anything at least 5 times more than any other BCS-like superconductor. And if you can double that, then you completely revolutionize the technology. You can have room temperature superconductors or close to room temperature. So that was really a driving force to understand. And soon after discovery of cuprates, there are other classes of unconventional superconductors are discovered. For instance, organic salts. And about 10 years, 15 years ago, iron-based superconductors. And if you want to know about iron-based superconductors, you can ask Puyan. He works on those systems. And a more recent addition to this family, though it's still controversial, is the superconductivity in twisted bilayer graphene, which I'm not going to talk today. But we discover new unconventional superconductors every day nowadays. So so I discussed why they cannot be BCS, but when you look at the phase diagram of these systems, you can see that they are very similar to each other. You usually have some kind of a magnetic order. In the case of cuprates, at the parent compound, when there's no doping, it's an antiferromagnetic multi-insulator. Whereas in heavy fermions and iron-based superconductors, it's an antiferromagnetic metal, usually. And it can be ferromagnetic metal too. In the case of heavy fermions, there are ferromagnetic superconductors as well. And in the case of organic salt, this does not really show any long-range order, so they write spin liquid. And as a function of some tuning parameter, this magnetic order is suppressed. Here, 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 and in this case, pressure here. And when you suppress this magnetic order, you have superconductivity. And of course, there are a lot of material-specific phenomena, which I'm not discussing here. Cuprates has its own controversies on pseudo-gap, strange metal, which again, I'm not going to go into details of all of this. I'm mostly going to talk about superconductivity. And so you might ask if the effective attraction is not due to phonons, and what gives rise to superconductivity. And again, this is still controversial, and there are different theories based on, they are usually near some magnetic order. So people think it might be due to short-range magnetic order, like short-range singlets. This is Anderson's idea of resonating valence bonds. This is more like a strong coupling theory, or in the weak coupling, there people think about paramagnons. Paramagnon means that magnon are the low energy excitations of magnetic systems. So paramagnon are like almost like a magnon, some collective excitation of things that does not really order. And you can see that most of these phases appear near quantum critical points where the magnetism dies. So people argue it might be due to quantum critical fluctuations, where near a quantum critical point, fluctuations diverge both in space and time. So one can apply to all, or different theories might apply to different unconventional superconductors, still under debate. But something to do with magnetism, I think at this point everyone agrees on. All right, so how do we find new classes of unconventional superconductors? Let's say I'm an experimentalist, I want to go to lab, synthesize something, which I am not, but let's say if I were. How can I find new classes of unconventional superconductors? And one of the route that people have taken is try to mimic the chemistry of cuprates. They want to make, cuprates is the most promising one that has the highest TC. Let me do things that does the main things of cuprates, and maybe they become superconductor as well. Any questions so far? All right. Okay, so what are the minimal things we want to distill from cuprates, such that if we want to make similar compounds, what do we need to include? So the cuprates have this crystal structure called Radelsson-Popper or layered perovskite structure, where the coppers are in an octahedral coordination of oxygens, and in the two-dimensional plane, they form a copper oxide plane. And these copper oxide planes are layered in between their fluoride slabs, meaning that it's not really two-dimensional, three-dimensional, it's quasi-two-dimensional. So we want quasi-two-dimensionality. And nominally, in the parent compound, when there's no doping, the copper is in a 2+ configuration. This is 3d9. This gives rise to a single hole in the 3d x squared minus y squared orbital. And well, the 3d orbitals are strongly correlated, so there's strong Coulomb interactions. And distilling all these three elements, Anderson, when these cuprates first come up with, said that the minimal model to study cuprates is the two-dimensional single band Hubbard model. And even though this is, of course, a toy model, and it's still questionable if one can reproduce all the different phases in cuprates by just using two-dimensional single band Hubbard model, the answer is probably not. But it's at least it's a good starting point, and probably is a good way to get a T-wave superconductor. So the goal is to mimic these three properties such that it gives rise to a two-dimensional single band Hubbard model. That's the goal. All right, so why nickelates? Why nickelates? And the answer is actually almost trivial. Nickel is next to copper on the periodic table. So if you want to form 3d9, what you just have to do is, instead of having 2+, you just need to have a nickel 1+. Okay. That's it. If you can make the same structure with nickel 1+, according to everything I discussed, it should be a superconductor. Then this raises the question, why did it take 30 years to find superconductivity in nickelates, if it is that simple? And the answer is actually this layered perovskite structure, this Radelsson-Popper phase in nickelates, turns out that is extremely challenging to synthesize and dope, because you don't only want to make the parent compound, you want to be able to dope it. So it turns out that this is a really, really challenging task. And even though it's been tried many times, clean samples that are doped, has not been successful. There are definitely people have been trying this for many years though. And there are other proposals of creating these three properties by artificially making thin films using molecular beam epitaxy, layering different, layer by layer, putting different nickelates that would break the, artificially break the cubic symmetry. But these theoretical predictions unfortunately didn't hold experimentally, because it doesn't produce large enough orbital polarization, meaning that you want really a single band. You don't want the other EG orbital. You want only the x squared minus y squared orbital. So this is why this mainly straightforward way of mimicking cuprates by using nickelates have been challenging to find superconductivity. Again, if you have any questions, just please feel free to interrupt me anytime. All right, so now we come to 2019. The Harold Huang's group from Stanford were able to grow the perovskite phase, the neodymium nickel O3, these thin films using MBE on top of strontium titanate, and using a technique called hydrogen reduction, they were able to mainly get rid of the apical oxygens. So normally this is the nickel side. It has 6 oxygens bonds. This is octahedral coordination. By hydrogen reduction, they are able to get rid of the oxygen in the North Pole and the South Pole. Okay, so this is a new phase of crystal structure, or a new phase of matter. Not in the terms of symmetry breaking, but it's a new material. Now, instead of neodymium nickel O3, which is a perovskite, now you have neodymium nickel O2. Okay, so this one you can clearly see that does not have the cubic symmetry. So this is one of the things that we wanted to do, get rid of the cubic symmetry, because we want quasi two-dimensionality. Does it lead to a single band? I will discuss it in a second. And when they doped it with strontium, so this is the parent compound without any strontium doping, is more like a metal, but the resistivity picks up at low temperatures, probably due to disorder. But when you dope it with strontium, the resistivity drops to 0, becomes a superconductor about 15 Kelvin. So this is the discovery, the first discovery of superconductivity in nickelates. And before I go any further to provide my theoretical understanding of this compound, I would like to address an issue that came up many times when I try to write papers or proposals on this compound, that there are multiple reports on experimental reproducibility. People tried to do the same thing, at least these 2 papers, and didn't find any superconductivity. And of course, this is a problem because the science is only science if you can reproduce things, right? But it turns out, growing these films is extremely challenging. It took like 5 years for Harold Wang to actually do this experiment, and to be expecting completely different groups to grow these in a few months is, it's not clear if their samples are clean enough. And at the same time, there are at least 2 other groups that have been able to reproduce these results and these papers. Okay, so other groups, these are not the samples sent by Harold Wang's group. These are other groups that are not connected to Stanford group that were able to reproduce these results. And the Harold Wang's group were also able to discover superconductivity in a related compound where the rare earth is not neodymium, but it's praseodymium, and they have similar theses. It's practically the same compound because the rare earth does not play much of a role. So even though there is controversy in the experimental reproducibility, as a theorist, I take these results as its face value, and I assume that the experimental results observed here are correct, because who am I to judge? They can do it. Some groups are able to reproduce it. That's good enough for me. All right, so let's move on.
Onur,
yes.
So what other parts of phase diagrams have been looked at? Like what other phases does it have? Is it clear?
It's mainly just a bad insulator, bad metal. So you can call this bad metal because this increase in resistivity is not really large enough to call it any kind of insulator.
Mm-hmm.
So bad metal everywhere,
mm-hmm.
and superconductor.
No magnetism?
No magnetism, and I'll come to that.
Okay.
Okay. So you're ahead of me. All right, so let's try to compare nickelates with cuprates, and let's see what are the similarities and what are the differences. So similarities, as I already discussed, it's quasi two-dimensional. Nominally meaning that if I do this simple count, I expect the oxygen to be -2, neodymium -1, +1, etc. This gives me a 3D9 configuration. But of course, in a crystalline environment, this is not necessarily true. once it hybridizes. But nominally, it's a D9 configuration. That's good. And we have a high orbital polarization, meaning that most of the electrons are in the dx square minus y square orbital. So these are the good things. It's similar to cuprates. But what are the differences? So as Puyan pointed out, the parent compound is not an antiferromagnetic Mott insulator, but a paramagnetic metal. I call this metal because this increase is not even twofold. It's just disorder, in my opinion. Or you can call it bad metal if you want. So this is a big problem because I've been telling you that the unconventional superconductors arise near a magnetic when you suppress magnetism. And at the same time, it's
sorry, another question. So like heat capacity, all of them behave like a Fermi liquid, or?
The heat capacity is, I don't think it's in their paper, okay. But the Hall coefficient, if you look at the Hall coefficient, it's for the parent compound, it looks like multiple carriers, so multiple bands, which again is the next slide. And the one that becomes superconducting looks like a single band for the Hall coefficient, which tells you about the carrier characteristics.
Okay, thanks.
And okay, so it's not the parent compound is not an antiferromagnetic insulator, but a paramagnetic metal. And this is very strange because if it is really 3D9, if it is a half-filled band, you would expect it to be a antiferromagnetic Mott insulator. How is it that it's not an antiferromagnetic Mott insulator? And here comes the main difference from cuprates. When you look at the band structure, here the red band is the dx square minus y square orbital. These are density functional theory calculations. And in cuprates, you only see this band, okay? So in cuprates, only this band crosses the Fermi energy. And that's why if you are in D9, it would be half filled. But in nickelates, there is an extra band that comes from the rare earth atom, neodymium, that has mostly these Z² characteristics. And that crosses the Fermi energy too. And that is partially filled. Okay? So this is one of the main differences from cuprates, that in nickelates, there is an extra band, which is weakly interacting because it has very low density, that crosses the Fermi energy and coexists with the strongly interacting dx square minus y square band. As a result, even though it's nominally 3D9, this leads to self-doping because some of the electrons go to this rare earth band. As a result, the parent compound is not really D9, it is self-doped, okay? It's actually less than D9. And also another interesting thing that first, I think, raised by George Shawartsky was that here you have a weakly interacting band coexisting with a strongly interacting band. This really sounds like heavy fermions, okay? And I will come to that mainly in the second part of my talk. So the questions that I would like to address is, and I should probably speed up a little bit. Is it possible to eliminate the rare earth band and make it more cuprate-like? Because if we want to make nickelates more cuprate-like, right? Is it possible to do something that this rare earth band goes away? And this is this paper. The second one is what are the effects of this rare earth band? Let's say I don't want to get rid of it. I want to study its effects. And can it lead to any new phenomena? This is the second part of my talk. All right, so for the first part, this neodymium nickel O2 belongs to a family of square planar nickelates with the general formula of this. And this is similar to perovskites. In perovskites, you would put different layers. For instance, lanthanum copper oxide is the single layer one. You can have 2-layer, 3-layer, etc. before you put the fluoride slab. And you can do the same thing in square planar compounds. You start with a Radhason-Popper series, let's say in this case trilayer, and you apply the hydrogen reduction, and it becomes now a trilayer nickelate, a square planar nickelate. So we picked the trilayer mainly because chemically it turns out it's the easiest to achieve the 3D9 configuration compared to bilayer or single layer ones. The experimentally observed one is the infinite layer, which is mainly, this is the perovskite version. And so this inclusion of these buffer layers which leads to quasi two-dimensionality is twofold. One is that because that rare earth band had mostly z-square dispersion, if you put buffer layers along the z direction, this reduces the hopping along the z, and therefore the rare earth band does not cross the Fermi level. This we can see in density functional theory calculations from my colleagues, where this is the infinite layer 112, where the superconductivity is observed. Here you have the rare earth band crossing the Fermi energy. Whereas in the tri-layer cases, this rare earth band is pushed in higher energies by mainly blocking layers to suppress the hopping along the z direction. And another effect is that and this is not necessarily intuitive at the first look, that the super exchange interaction is in this case higher because the charge transfer energy to the oxygens is reduced. And I don't really have much of an intuitive understanding other than that just we can look at the position of the oxygen bands. It's here it's closer to the Fermi energy, and therefore the super exchange is expected to be large. So two things. One, it gets putting this buffer layers, gets rid of the rare earth band and makes it more cuprate-like. And also it reduces the charge transfer energy, which gives rise to higher super exchange coupling. And in our modeling, we take the tight binding parameters from DFT, the super exchange parameters from both DFT and experiments. And here for the tri-layers, note that the super exchange value is actually quite large. It is in some sense comparable to cuprates. And we drive a TJ model, which is pretty standard in this field by projecting the doubly occupied sites in the strongly interacting band. Not going to go into details of these. Happy to discuss further later. And we do a slave boson mean field theory to solve for superconductivity. And again, these are pretty standard in this field. So what we find is, we find that the superconducting gap is much larger in the tri-layer compared to 112s, both because the super exchange is large, also the fact that there's no rare earth band here also enhances superconductivity. And we estimate the TC near half filling. The TC is set by the boson condensation of the slave bosons, and at high doping, it's the BCS condensation. And the real TC is determined by which one is the lower, so this gives you roughly a dome. And our calculations estimate a maximum TC about 90 Kelvin. All right, so this is the summary of the first part, which tells that if you make tri-layer nickelates, you get rid of the rare earth D band at the chemical potential. And this makes the system much similar to cuprates than the 112s. And then we expect the TC to be larger, mainly because the super exchange is enhanced due to lowering the charge transfer gap. Any questions?
So the tight binding model, you directly do it for the 3-layer, right?
Yes. Yes.
Okay. Because I was thinking that if this is really getting to the cuprates, can you like integrate out some bands and get an effective Hubbard model with the same number of orbitals, or it's not?
Yeah,
really?
it is mainly, we still only have the nickel dx square minus y square orbital, but there are 3 of them. And that's actually important in the trilayer cuprates too, that leads to some bonding, anti-bonding orbitals. Mm-hmm. And leads to some different orbital occupancies. So here you can see these are the 3 different orbitals, and they have very similar gaps because the splitting between the bonding, anti-bonding bands is not that big.
Mm-hmm. What about magnetism?
So magnetism, we anticipate magnetism to arise if you can actually electron dope the system and go to nominally half filling. But most of the studies are, because the parent compound is not really D9, it is self-doped away from D9. And if you really want to observe magnetism, you need to go to the anti-ferromagnetic multi-insulating limits, which in this case would arise in electron doping. But there's not many experiments there.
Yes, but you projected out the weakly interacting band, right?
Right. So at half filling, we would have magnetism. But
okay.
Yeah,
okay.
Yeah. But the way we treat we do an SPN representation for the spin, which gives right to at half filling a spin liquid rather than an anti-ferromagnetic multi-insulator. That is a problem of the large N limits of the theory.
Yes.
All right. So then the next topic is, okay, so if you want to make it more cuprate-like, go to trilayer, but maybe this extra band is interesting, gives something new. So what is the effects of this extra rare earth band? Can it lead to new phenomena? So this is what I want to talk in the last 10 minutes. And so now we do not necessarily a model particular to nickelates, but a more generic model. So what happens to a correlated band that is coupled to weakly interacting electrons? And so again, this sounds very much like local moments plus conduction electrons equal to heavy fermions, but we are in a different regime. We are not really heavy fermions with fully localized moments. We are interested in correlated metals that has valence fluctuations to some weakly interacting band. So this is more like a TJ model that is coupled to a bath, if you wish. That is the model that we want to study. So not going to go to the details here. Again, we are projecting out the double occupancy in the strongly interacting band. And pictorially, it's like you have a TJ model, which has like this singlets, but and holes, let's say. But apart from that, now it's coupled to a bath, so the electrons can leak to the bath, or they can interact with a Kondo interaction with the bath. So this is the model that we are studying.
This bath is not bosonic, right?
It is a fermionic bath. It is to mimic this this bath that comes in these systems where there's some extra band that is in some sense coupling with the strongly interacting band. So mimic this extra band, the rare earth band in nickelates. And once again, we are doing for the spin, we are doing a symplectic large ends representation for the spin and combine it with slave bosons. And we decouple it in every channel and solve everything self-consistently. Right, so before I go to the results, mainly we identified 3 different regimes. So the first regime is the weak coupling to the bath. In this case, if the coupling to the bath is very weak, practically nothing happens. We still have a TJ model, one band TJ model. Then we have a very strong coupling to the bath. And in this case, we have a very strongly hybridized bands, but effectively you still have a single Fermi surface. And at the intermediate coupling, when the coupling to the bath is order 1, then actually we fall into a two-band picture where both bands become equally important. And in general, when we are in this region, we find a large domain of stability for s+id pairing. And this is our main result. So how does this come about? So these are the real calculations. You can see as a function of the doping mainly, the NF is the density of the strongly interacting electrons. We find that as we increase the coupling to the bath, so this is the V wave amplitude, this is the S wave amplitude. The S wave amplitude starts to pick up when coupling to the bath becomes order 1. So when the coupling to the bath is small, it's again D wave as usual, but for large enough coupling to the bath, both S and D wave orders are present. And I would like to mention that this S wave is not the on-site S wave that you would get in a BCS theory. This is extended S wave that has the form of cosine kx plus cosine ky. And when we look at the, okay, so S wave is usually stabilized around half filling. And when we look at the phase between these two order parameters, there's always a net pi phase between them. So the total order parameter is s+id. There's a net I between them. All right, so what are the properties of s+id pairing? Well, because it has I in it, it breaks time reversal symmetry. So its time reverse partner is not itself, but it's s-id. So it breaks time reversal symmetry, breaks the point group from C4 to C2. So normally we have a square lattice. This breaks to, that has a pi by 2 rotation, that breaks it to C2 rotations. So this is equivalent to a nematic transition. And even though both D and S waves are gapless, they have nodes. S+id, it's when you have combined them with this form, is actually fully gapped. And
Onur, S wave, how S wave has nodes?
This is cosine kx plus cosine ky. It's extended S wave.
Extended S wave. Yes. Okay.
So yeah, so even though S and D wave have nodes, S+id is actually fully gapped. And so this is a quite exotic type of pairing. And as far as we know, there are only very few systems that have been suggested to be S+id, and not clear if there's anyone that's fully proven to be S+id. And for instance, in iron-based superconductors, there are proposals of S+id pairing. All right, so let me tell you a little bit about experimental connection, if what I've been telling you has anything to do with experiments. So the tunneling experiments on this nickelates found two types of pairing. This is, you come with a tip and you look at the density of states, okay? And depending on where you put the tip, they find either V-shaped density of states, which gives you D-wave superconductivity, which is related with D-wave superconductivity, or in some cases, they find fully gap superconductivity. This is very strange because normally if you have a uniform phase, you would expect the same type of density of states everywhere. But in particular, having two types of superconducting orders coexisting is quite unusual. And this does not prove that it is S+id, but it is in agreement with it. And the fact that part of it is already D wave and becomes fully gapped all of a sudden, excuse me, and becomes fully gapped all of a sudden suggests that it's probably not a regular S wave. So we cannot prove other type of pairing. For instance, D+id will give you fully gapped as well. So we cannot, it's not a smoking gun experiment, but it is very encouraging that actually our results might have resemblance in nickelates.
Oh, no, but this is a spatially resolved. A different position on the sample give you different,
yes.
Right?
So
and
suggest that they are close in energy.
Okay.
That you know, in some certain, there are patches of different type. I mean, experiment says that there are patches of D wave coexisting with fully gap superconductivity. That's what experiment says. And it's not clear what this is. And if they're close in energy, you expect this one to be D plus something. You don't expect a completely different channel to overpower. But again, it requires further experiments to see.
Also, are these samples a single crystal or they are multi-crystal?
They are thin films. They are thin films, and
Okay.
they are definitely very dirty. It's very, very challenging to make clean samples of these, mainly because this hydrogen reduction process really creates a lot of disorder.
I see.
That's one of the reasons why there's experimental, you know, controversy on reproducibility.
Mm-hmm.
All right, so this is the first connection with experiments. Again, we cannot really say, but it is actually quite encouraging.
Sorry, when you said BCS fitting, you mean with an s+id BCS theory or just S, right?
They fit to a fully gapped superconductor. It doesn't matter.
Doesn't matter.
Yeah.
Okay.
This is experiment. I didn't do the fitting, but they fit to D wave versus fully gapped. All right, the second experimental connection. I've been telling you that this really sounds like a heavy fermion. So let's look at heavy fermions. So uranium beryllium 12, not 12, 13 is a D wave superconductor. This is well established from every experiment. It's a D wave superconductor. And upon thorium doping, it actually, there's a second phase transition here. And it's been well established that this below the second phase transition, it becomes fully gapped. Okay. And for many years, okay, came originally with Kumar and Wolfe that this might be an s+id pairing. And they mainly did a Ginzburg-Landau theory. And if you have S and D existing, Ginzburg-Landau theory will give you s+id. This mainly like a Josephson coupling between two order parameters. And so in their case, they just did the Ginzburg-Landau theory. And our calculations provide a macroscopic realization for such a state. And of course, uranium, we are not saying what we did fully explains uranium beryllium 13. It's a complicated material with spin orbit coupling, different uranium multiplets, etc. Has some non-Fermi liquid behavior, two-channel Kondo effect, etc. It is complicated material, but you know, our mechanism having this two, mainly having this intermediate coupling to the conduction electrons, quite generically gives you s+id pairing. So it actually gives you one way of generating this fully gapped pairing from macroscopic calculations. All right, so this is the part of the summary of the second part. And so just to repeat, we consider the correlated metal that is modeled by a TJ model coupled to conduction path has a large tendency for s+id pairing, and which breaks time reversal and rotational symmetry and is fully gapped and might be related with nickelates and heavy fermions. All right, I think I don't have time for the extra part, so I will just conclude here.
Thank you.
Thank you.
So questions?
I have a question. Any isotopic effect is observed or not?
Can you repeat?
Is any isotopic effect on BTC?
Isotopic, I see. Not that I know of. Again, There are right now only 3 experimental papers on this system. I mean, there is more coming in similar family of compounds, but I don't think people try to see if there is an isotope effect to see if phonons are related. So I don't think there is. Again, you know, the TC is 15 Kelvin. It doesn't really rule out that it's not a S-wave superconductor. The MgB2 has 40 Kelvin TC, so it can still be a conventional superconductor. We cannot, I mean, more experiments needs to be done, but the fact that it's a very strongly correlated system, etc., we anticipate it to not to be a BCS type superconductor.
Any other question? So if there's not, let me ask. So you said that there is no single crystal, basically, right?
There are bulk samples which do not see superconductivity, and then they believe that in the bulk samples, when you do the hydrogen reduction, hydrogen enters inside the sample and messes up the.
Yeah, because I was thinking about the ways that you can see the signature of this s+id, like any types of edge state phenomena. Like, you know, we have proposals for extended S wave. There is clear experiment and lots of works on D wave, edge states in D wave, which confirm the edge state, or some sort of fancy Josephson junction, which for D wave, which was basically connecting the 2 edges of the D wave and showed the D waveness. So I was asking is the crystal glow grows in this material to a level that one can think about those probes?
Yeah, yeah, I think not at this point. I think, but I mean, it is a very rapidly growing field. And as I said, more experiments are coming. So I think hopefully soon enough, this many controversies will be, you know, resolved on pairing and symmetry and yeah. But I mean, the s+id does not have chiral edge states. D+id does.
Okay.
So s+id, I think, does not have edge states. But
okay.
Yeah, I think it does not, because in D wave and extended S wave, it originates from the Dirac point, which is not present in s+id.
I see. Yeah, and also, other than superconductivity, is there any other phase which is puzzling? Observe. I guess there are not many experiments yet to say, but
yeah, all the rest of the phase diagram upon, you know, strontium doping, they just see a bad metal.
Okay.
And if they do electron doping, then they should see an antiferromagnetic mode insulator. But I think people are more interested in superconductivity. So
I see. Okay, any other question?
I mean, but the normal state is probably a non-Fermi liquid.
In what sense? In terms of temperature dependent resistivity? Okay.
Yeah, if I will have to go back all the way back, but the resistivity looks pretty.
Even the temperature dependence of resistivity, right?
Yeah. Stop. Still going. Sorry.
Okay, that's okay.
Here, so you can see that it's pretty linear. Before some Anderson or weak localization picks up.
Right. Okay, thank you.
Thank you.
Okay, so if there's no specific questions, of course, we can continue discussion with Onur for a while, but if other people want to leave, please feel free. So thank you, Onur, again.
Thank you.
So thanks. This is interesting. This issue of the 2 bands, one strongly correlated, one not correlated. I was also interested for a while with Sarang, you know, when there was this story of a strain graphene that you well know, that gives this Blondeau levels, right? So that gives you an effective magnetic field for the two valleys, which has opposite sign in the two valleys, right? So what we were thinking was that what if we put this system in an actual extra magnetic field, okay? So that in one valley, that field can cancel the strain-induced field, and in one valley, it doesn't, okay? So you get one valley, which is kind of a flat band, and another valley, which is a Dirac band.
Yeah, that is interesting. Never heard of that, yeah.
And then we wanted to think about, okay, is there any novel phenomena that can emerge if you have one flat band and one Dirac band, which we didn't really follow up.
Yeah, that is definitely interesting.
Yeah.
I think whenever it becomes fully flat, usually ferromagnetism is the most favored one.
Right.
But it depends on your feeling, I guess. You can, I mean, you can
but
think
then
about.
How is it modified when you couple this to a dispersing band?
I mean, that is really like the Kondo lattice model, right?
Yeah. Yeah. Okay.
So in our case, the parameter regime that we pick is such that our band, strongly interacting band, is not really flat. It's like a correlated metal. And that actually makes a difference, because then you can reach to this intermediate coupling regime, which generates this s+id pairing.
Okay, I see.
If the band is completely flat, then you are always in the Kondo limit, which is the large coupling.
Right. Right. Okay.
And then that, you know, has many people studied that problem.
Also, is there any work on trying to build a 3-layer nickelate?
Yes, there are works on it. Yes, not a lot to talk.
Okay.
Onur?
Yes.
Can you tell me a little more about what you meant by it's a bath versus a coherently coupled system? Where is the distinction?
So distinction between bath and what?
When you call it a bath, what do you mean actually?
What I mean is it's really a fermionic bath, and it originates from this band. So that is what I mean. And the difference between the heavy fermions and the model that we consider is in the parameter regime. In some sense, both are two-band Hubbard models, right?
Okay.
So the parameter regime that we choose is to more mimic this system, that the strongly interacting band is not really completely flat, but it is like a TJ model, and that is mainly the difference lies only in the parameters.
Okay.
I think what Alex is asking, like in what parameter regime you have a bath, in what parameter regime you have a heavy fermion physics. Yeah.
Right. So let's go to that then. So this is the model that we study. And this is, again, just comes from projecting the double occupancy of the strongly interacting band. And mainly the three regimes here are when this T, if your strongly interacting band is flat, completely flat, like heavy fermions, then you are always in this strong coupling to the bath regime, which gives you effectively a single band picture of strongly hybridized quasi-particles. To be able to, mainly in this intermediate regime, if you're familiar with heavy fermions, there is a concept of indirect band gap, not the direct one, but the indirect band gap, which gives you the Kondo temperature. So in this case, that one actually collapses and goes to negative. So this would be your indirect band gap, but that goes negative. Therefore, you end up having two Fermi surfaces. And this, and both are, even though this two-band regime, these two bands that you get, this effective two bands that you get, still are very strongly interacting. It's not that one is weakly interacting, the other one is strongly interacting. It is still very strongly interacting, but the indirect gap collapses in this regime, which is not something that is common in heavy fermions.
Right. So in the BCS pairing, in the intermediate coupling, when both bands are equal, you have this additional possibility of s+id because you can pair between different bands, or?
It's actually, it is still it is not an interband pairing. It's still an intraband pairing. But I mean, one of the ways to understand is just fermiology. One can draw the bands where they cross and then draw the gaps. The D wave would have line nodes and the S wave will have like nodes like this. And if you have this two band regime, you can show that the S wave pairing is energetically comparable to, normally the S plus extended S wave is not favorable because its nodes lies on the, no, the extended S wave is like a diamond, yeah. So its nodes lies on the, like the half-filled Fermi surface. And in this case, it becomes energetically favorable because one pocket shrinks near the gamma point, the other one goes to the M point. So wherever the nodes of the S wave, there is no quasi-particle, so it becomes energetically comparable to D wave. I don't know if it helps, but we are not really doing BCS theory, but one can understand some limits of it from just doing a fermiology as well, just looking at the Fermi surfaces.
What prevents you from just to first order doing a BCS theory on the Hamiltonian that you wrote?
Yeah, it is to start with, it's a very strongly interacting system. We already projected out double occupancy. And so we start with a system that does not allow double occupancy.
But you need that for extended waves, right?
Not necessarily.
You can have on-site and get extended.
You can have attractive interaction, and if your Fermi surfaces looks like, you know, if your Fermi surfaces are such that they do not really overlap with the extended S-wave Fermi surface, for extended S-wave nodes, you will energetically be okay with picking extended S-wave. Actually, in the single band Hubbard model, the extended S-wave is not so far away from D wave and becomes favorable upon high doping, which is not really observed because at that limit, the TJ model approximation breaks down. It should only work near half filling. But in principle, if you take this approximation and go all the way to very high dopings, the extended S wave is actually becomes lower in energy than D wave.
Okay, thank you.
Sure.
Thank you, Onur.
Sure.
Very interesting material.
Thank you.
We can talk more later. Yeah.
Absolutely.
Yeah.
Okay.
So I'll be in touch about the other stuff.
Okay.
Yeah.
All right.
Yeah.
Looking
okay.
forward to it.
Yeah.
Okay. Thank you again.
Thank you.
Thank you.
Thank you.
Bye.
Bye.